надамо йому слово.
The next speak will be as well performed by our foreign guest, Gintaras Valušis. I would like to welcome him. He is the participant and the co-author of our common research project of NATO project. So, Professor Valušis, you are welcome, please.
Hello, everyone. Before proceeding to my talk, I would like to express highest possible appreciation for organizers of the conference, allowing us to share what we're doing in TERAHERTZ and also share our common interest in NATO projects. I think that is the first. We have no one. I believe that soon we'll have next projects which bridge our institution to the common work and complementary expertise in the field. So my talk will be dedicated to TERAHERTZ structured light, in continuation of TERAHERTZ topic, which was nicely given in a previous one. But my talk will be mainly dedicated first to imaging, since we started from them, and then we'll go to what we could expect of application of TERAHERTZ structured light in TERAHERTZ communication. So first, introduction of structured light features. Then we'll go to the terahertz beam engineering using silicon diffraction optic components. Then we'll go to the structured light applications, in particular giving attention to IR beam generation, which allows us to make a curvature of the beam, and also some words about non-paraxial optics. And finally, I'll go to structured light application in terahertz communication. So, in fact, before proceeding, I would like to start with a structured light. It means it is electromagnetic waves with a strong spatial homogeneity of amplitude, phase, and polarization. And if I look at the several review articles, it's a very nice picture showing how beam looks like. If I look at the beam, which is Gaussian, it means that I have very nice beam profile. However, I can manage it making inhomogeneous distributions in a space like a Hermitian Gauss beam, like Langrenn Gauss beam, and something like that. So in fact, the structured light, it's important science for light engineering, and in particular, it can be dissolved resolved in a space first, when the beam have spatial inhomogeneous structure and also evolves in time. So it can be nicely illustrated from laser applications because we have a coherent light, and also it means that in the output I can have like Gaussian mode, while in the output I can have very different kind of modes which have different structure in space and also evolves in time. Our research started from absolutely different topic. We worked in terahertz imaging, and our initial idea, what we see here, is just to remove big components from optical setup first, and also try to make beam engineering allowing to see inside the thin objects, which are not simple envelopes, not simple boxes, but they have relatively thin, more than 20 millimeters of thickness. So idea was first to replace parabolic mirrors to the flat optics, and silicon diffractive optics can be one of the ways to go. An example is Fresnel zone plates. So that's a way to go, and allows us just to make system more friendly user and probably more compatible and more easy to implement to real experimental conditions. So our approach was different from not chemical way, not micro machining way. We used laser direct writing techniques. We are using light conversion lasers mainly, and to make as a ablation technology as our main tool to produce silicon diffractive elements. And you see the profiles, the photos, how it looked like after a relevant investigation, selecting precisely technological conditions. Most important result here is that how many zones we should need to use and have an optimal signal. And we discovered that our main optimal conditions is around 8 zones in a silicon optics. It means there's good compromise between technology and time-consuming work needed using to produce such kind of elements. So light engineering and the first structural light application can be used like Fibonacci sequence. It's known in optics, and Fibonacci is known for visible because the main feature is to have a bifocal operation instead of a single point, a single focus. So in fact, if you compare Fresnel zone with Fibonacci zone, we can see here we have bifocal operation, and the distances ratio between them is exactly coincides with the called golden ratio in optics. So it was not in optics, but we decided to do it in imaging, and our approach is just use the same technology for lasers, and instead of Fresnel zone, we have bifocal operation, allowing to see how it looks like. And we have 2 focus, and idea is to use it first for imaging purposes. So we did it the same technology as in Fresnel zones. And what we see here is 2 focal operation here, and one of these focus is more expressed and it looks slightly lower in intensity. But if we look at the application for the different specific kind of sample, which have 7 millimeter thickness, and different things are glued in different planes, we can see the different imaging, and this allows us to see in both objects with a good resolution and with good signal to noise ratio, and the things are just glued in different walls of the subject. So in fact it's good point for applications, in particular for imaging, but our idea is to go further because it's 2 focal points. It's not good enough, in particular when we have movable things inside the optical packages. So idea is to see, is it good for resolution in comparison with the wavelengths? In fact, what we have here is a resolution is close to the wavelengths. It's pretty good, but idea for applications is to connect them in both focuses in a one like needle shape, and optic is known like needle shape beam is called Bessel profile, which can be done and can be applied for imaging purposes. Once again, we're going further, and our approach is very similar. I mean, in optics, this can be done using a special kind of hexagon, allowing to manage the phase of the coherent light and to extend the focus in certain range. And our focus was about to go more than 10 millimeters in a focal depth. So hexagon can be done in such a way, and you see very different profile. Every step is dedicated to manage the phase in different spatial areas, and our results was the same. Silicon optics, very good option for TERAHERTZ because it's transparent and it's much more convenient to use it. So once again, what we did, it's you see the profile here is focus is 4 phase levels, and focus we expect up to 20 millimeters, and here the photo how it was done using laser ablation technology. So our frequency range is 600 gigahertz, is particular range for security, not for communication at the moment. So what we did is just measure profile and to see how it fits for our aims. It seems that we have pretty good surface, and it seems that laser ablation technology is a good tool to do it. And what we did first is simulated and measured vessel beam profile. What you see here is needle-like shape, which extends pretty well, and we'll see its experimental and simulated data. It means it should be very distinctive. And here is a normal conventional Fresnel zone planes, whilst in a black color we see vessel beam. So if we look further and you see how it operates, so idea is the following: to see the resolution first, and is it enough for imaging purposes? And what you see here is a specific kind of sample allowing to see the resolution. What you see here is operation and goes to the range of the wavelengths. It seems to be good application point. However, we also worried about not only resolution, how much we can win in signal to noise ratio. For that aims, we applied the convolution to extract good resolution and to increase signal to noise ratio. So result and our beam measuring setup is the following. You see there is any mirrors, only silicon optics. And here is special kind of sample which have three-dimensional printing. It's plastic stuff which have a variation of 4 different kind of plates consisting of slots, and we have variation in the thickness starting from 3 millimeters up to 12 millimeters. And what we see here, how it operation range, the comparison of vessel beam and conventional Fresnel zone plates, we see increase in signal to noise ratio, and it seems to be that it's good a way to have an extended focus, and it can be well suitable for terahertz applications. So what we can do further, so before we did bifocal, then we made vessel beam, and the next step will be slightly exotic, and we have aimed to first not only to apply for imaging, but also to learn optics a little bit more. So it's just go the beam over the corner. I mean, to go over the wall or over the corner, like in football, you know, the beam goes as the ball comes in curvature, in curvature shape. So curved direction of terahertz beam, once again, silicon optics, once again will be later technology, but also its extension of the previous idea used in conventional visible regime, so-called IRI beams, which are usually have an acceleration feature. It means the trajectory is just curved. And it is known in optics, and it's interesting results mainly apply to laser ablations and to manage the beam when you use a very powerful beam to fabricate different kind of structures. And so description from mathematical point of view relies on the IRI wave function, which looks very complicated, but the result is very exotic, and the beam can be decomposed in different structure in the space and evolving in space as well. So it's many families in this, like Weber accelerating beam, Bessel beam, Matteo beam, and so on. So we are restricting our focus mainly in IRI beam, useful for terahertz terahertz imaging first. So it looks a different shape. You see here is also product of laser ablation technology. The zone plates, IRI zone plates, look like this one. And for this case, we called its phase profile is cubic. And this transmission and transmission function looks relatively complicated. And also this description of linear phase functions, just to see with in comparison to Fresnel zone planes, is totally different. And what we need to do is just to make a good zone plates following exactly mathematical predictions and precise modeling of the element. Once again, Ferrous laser from light conversion, 150 femtoseconds with average power of 5 watts and 50 kilohertz repetition rate. So theory is relatively complicated. We solved it numerically, Sommerfeld diffraction integral. Our result is beam generation. Also, no mirrors, no any bulky elements. Only IRI zone plates here, and here is IRI and zone plane, and this is our detector. Detector was CMOS-based transistors operating at 600 gigahertz. And what we see here is very similar picture, which was also known from visible stuff. We have terahertz structured light generated by purely silicon diffractive optics, and they have had structure and propagation features exactly with the visible. So as you see here is in large view, it's possible to see so-called deviation, like parabolic shape along the optical axis, and here is inversely visible light. Here is so-called inverse trajectory, which goes 1 over z along the optical axis. So it's the features of IRI beam. So what is important here is it possible to do good imaging here, and how it operates with the resolution. So first we have as the same object target produced with different kind of slits, and we applied IRI lens to see the optical features here, mainly restricting ourselves to resolution features. Scan was made along this different kind of slits, and to see how it evolves. So you see there's imaging here. And important stuff here is pronunciation of peaks related with the diffraction here. So depending, it's tricky optics. It means IRI lens, it's not enough sometimes, and we need to use a zone conventional plane to collect the light. What we see here is images of this target and their features, how it looks like. So if I apply a zone plate in addition to IRI lens, I have better resolutions. Which in pure case, we have T3.2 lambda, here we can go in a better 1.6 lambda. So in fact, this is quite enough. Since our frequency is 600 gigahertz, his spatial resolution is quite enough to apply it for imaging aims. So if we try to make a benchmarking and try to use and to prove the curvature of the beam, we place it just object, and try to cover part of them, 10%, 30%, 50%, and finally 60% of object using IRI beams, and also Bessel beam for comparison. So if we look at this point, it means in the terms of resolution and contrast, you see still good operation point, and in particular, when the big part was covered, still we have good operation of IRI beam, and also it means that we can see the signatures over the objects over the wall. So in fact, it's good results, and it could be used for security aims. So idea was not only used for security, it's just, is it possible to use this feature of IRI beams and for material diagnostics? And one of our results is just to show the graphene layers placed on the high silicon substrates. Once again, silicon is transparent, while graphene, different numbers of graphene can have different electrical properties. It means since the electromagnetic wave see as this electromagnetic wave functions, it can be done, and maybe it's possible to see how it looks like in terahertz. So initially we did Raman scattering to see how the quality of graphene. We plotted 2 peaks, which usually used in graphene characterization. It's what optics just served as a test on the quality of graphene layers. And one way we go to terahertz, we see totally different approaches. Here is the results. We plot them, and here is we see these graphene layers, and we are measuring a different kind of we're measuring imaging. Here it is varying the thickness from 1 graphene layer to 5 graphene layers, and silicon substrate served as a reference. So if we plot this as a number of graphene layers and the zone plate, conventional zone plate operation, and also Arizona plus zone plate operation, we see strong difference. And this strong difference related with a certain kind of non-monotonical behavior in transmission when IR beams just incident on the layer. So question is why? Because we do not expect this in previous experiment. So it is Gaussian mode, and IR or terahertz structured light in the form of IR beam has displays totally different behavior in two-dimensional material inspection. So we made a modeling then, and idea was to see what happens when we have a graphene layer on silicon. We applied mathematical model for S-polarized terahertz light and P-polarized terahertz light, and what we see here is a ratio between the polarization. What we see here is absolutely different behavior of refraction index with respect to polarization. It means since you have very high numerical aperture, our structured light feels totally differently graphene layer properties in comparison to Gaussian modes. So we did a separate study on that on terahertz structured light, and we published big paper in Light Science and Application. So, but what is important here as well, since when we have a silicon optics placed on 500 micrometers thickness substrate, we have a little bit different approach in optics. So it's called non-paraxial optics because numerical aperture is very higher. So in terms of imaging, we should talk about modulation transfer function, which usually represents ability of the system to produce a contrast as a functional spatial resolution or spatial frequency. So in fact, of silicon optics for that kind of 0.6 terahertz, so modulation transfer function in normal case could be described very similar way like in classical optics using conventional lens formula. But when we go to non-paraxial optics, it means our picture is strongly disturbed. This formula becomes not valid, and in our beam becomes a resolution or modulation transfer function becomes disturbed because of non-paraxial origin of the light when propagating through the media with a very high numerical apertures. It means from mathematics that this formula becomes not valid anymore. And the depth of field and depth of focus in Gaussian modes and IR modes, it becomes different, and the best constant and the best resolutions areas become decoupled from each other, saying that non-paraxial optics is totally different in comparison to conventional using in imaging. So now we're going, what can be advantage of terahertz structured light in communications? And we represent just several results, just currently very hot topic now. And we talk about 100 about communication exceeding 100 gigahertz. An interesting work by Daniel Mittelman group from Brown University. It means we're talking about two areas now. The first one is 5G, what we have currently, and we talk about one spectrum, which is around 150, and very recently, its big attention got spectra from 250 up to 320. So what we have here is a lot of interesting stuff, how we can transmit so big frequencies in big ranges. And usually, if you look at the lines and the non-paraxial, non-structured light propagation, this z-axis you see is in millimeters, not meters like usually in conventional beam, conventional communication system, but only millimeters or up to 1 meter only. So in fact, we have Gaussian mode, we have Bessel mode, and here we see the same RD beam, which is used can be used for communications. In that case, when we have only small distances, we usually talk about near field communications. So what we can have is it possible to apply, let's say, structured light in communications? It's a very recent result using Bessel beam in communication system, just indication how it works. It's the same hexagon, and you see the transmission distance only in centimeters. So range of communication at the moment is only below 1 meter, and the approach is just transmitter, which is seen as obstacle here. Obstacle is this wet textile, and then is hexagon, 3D printed hexagon, which being placed on the Gaussian beam to produce Bessel beam. And what we see here is Gaussian beam with blockade, which is cancellations, which is very, very poor resolution. And then when we're applying this Bessel beam, blockage can be certainly removed, and we see a much better resolution in emission picture. So very recent paper which just appeared a month before. It's also done in Mittelmann, also application of, let's say, structural light in communications. Once again, IRI beam, but now is in communication approach. So once again, distances are millimeters, not very long, and here is the curvature which represents this IRI beam propagation stuff. So what people did is they're applying 300 gigahertz again. It's communication, and also blocking, moving the blockade as a block to block the beam for Gaussian mode first. And here's it also trying to see how it operates with IRI beam. So initially, what they did is it's a movement of emitter, and then they placed linear phase plate. It means it is conventional Fresnel zone plates to make a beam illumination. There is no curvature. It means we see very, very weak signal. But when you replace it with a cubic phase, which is usually IRI beam, we have very nice curvature, and it allows to see very well resolved signal in a communication channel. It's a number of stuff was done trying to see how the IRI beam properties, variance of frequency can be applied. But once again, the distances are pretty low and still not exceed several meters. Here is a good indication only about 30 centimeters. So in fact, it's hot topic and seems to be really more discoveries. And the further steps is related with the longer distances, because even several meters, it's not enough to provide next generation of communication first. And the next one, how we can make an optimal optic solutions, because arrays and antennas becomes relatively large in comparison to the compact stuff. So it means it can reach up to 1 meter. It means in case we want to extend the operation distances, let's say 200 meters only. So in fact, there is a lot of challenges, a lot of interesting activities, and we can expect interesting application in this area as well. So my outro and summary will be following. So we applied different kind of structured light for imaging first, and we disturbed that it can be done using purely silicon-based diffractive optics without using any bulky mirrors in light engineering and in that application in imaging system. We demonstrated with Fibonacci and Bessel imaging usually purely silicon diffractive optics, and also shows that non-paraxial tertiary structured light in the form of IRI beam can be successfully applied not only for imaging but also for two-dimensional materials inspection. And finally, terahertz structured light is gaining strong attention in communication, and we could expect attractive exploration and processing application in creating new generation of communication network. Thanks again for your invitations, and thank you very much for your attention.
Спасибо, профессор Valušis Gintaras, за интересный доклад, тоже в терагерцовом диапазоне, который, как мы уже сегодня несколько раз говорим, является одним из приоритетных в мировой науке, в том числе и отмечено это на Всемирном конгрессе, который будет буквально через несколько недель проходить в Соединенных Штатах Америки полностью в дистанционном режиме. Спасибо за ваше содержание, которое мы услышали в рамках этого доклада. Ну и спасибо за то, что мы с вами начали уже второй год сотрудничество, совместно выполняя один из проектов научного совета НАТО. Спасибо.
Professor Valušis, we would like to thank you for your report, very comprehensive and interesting report that is as well devoted to the TERAHERTZ diapason that is very popular nowadays. And as well, we would like to thanks for the cooperation. For almost 2 years, we are working in common on our joint project, and we hope that this cooperation will last for long more years. Thank you very much.
Thank you very much for your attention and your invitation as well. Thank you.
Thank you. Thank you. На прохання учасників конференції ми міняємо послідовність докладів. Зараз спочатку 4-й по програмі, а потім 3-й.